Hello. Today, in response to a request from a YouTube viewer, I'm going to give a little more information on standing or stationary waves. I have already covered the issue of waves, travelling waves and standing waves in my video Waves A-Level Physics, and the link to that, and in particular the standing wave section, is on the screen now. Before we look at standing or stationary waves, we first need to consider travelling waves. The formula for a travelling wave is that y is equal to the a, which is the amplitude, times the sine of kx minus omega t. I'll explain what all that means in a moment, but if we plot that graph, we will find that we get a sine wave, and the sine wave itself will travel. That's why it's called a travelling wave. It will move in this direction. We'll see in a moment that it doesn't really move, it just gives the illusion of moving, but we call it a travelling wave. We've already said in previous videos that the distance between two peaks is the wavelength, lambda, of the wave, and that if you take a fixed position and you watch to see how many peaks go past in 1 second, that is the frequency, the number of peaks passing a fixed point every second. I should perhaps have explained that in this graph, this is the y-axis and this is the x-axis. The period of the wave, which is sometimes written as t, is equal to 1 over the frequency. The period is the time taken for one wavelength to pass the fixed point. So the frequency is the number of waves which pass in 1 second. The period, t, is the time taken for one wave to pass the fixed point. In other words, starting here, when this crest reaches this point, the time taken is the period. And finally, as I said, this entire wave is moving to the right in this way, and it is travelling at a velocity v. And we will be able to calculate the velocity in just a moment. Now this formula, we shall see, tells you everything you need to know about this wave. K in the formula is equal to 2 pi over lambda, where lambda is the wavelength. And omega in the formula is equal to 2 pi times the frequency, where frequency is the number of waves passing a fixed point every second. Now the velocity of a wave, that's v here, is given by the wavelength multiplied by the frequency. And the wavelength, you can see from this formula here, the wavelength is 2 pi over k. So the velocity is the wavelength, 2 pi over k, times the frequency, which we get from this formula. Here the frequency is obviously omega over 2 pi. So omega over 2 pi. The 2 pi is obviously going to cancel, and that simply gives you omega over k. So when you have this formula, that y equals a sine kx minus omega t, then the omega and the k give you, omega divided by k, gives you the velocity, the speed at which this wave is moving to the right. I should just explain that the minus sign in this formula indicates that the wave is indeed moving to the right. If that were a plus sign, it would mean that the wave was moving to the left. We can even measure or discover the momentum of the wave. In our quantum mechanics videos, we've established that the momentum is Planck's constant divided by the wavelength of the wave. And that came from our quantum mechanics videos. Well, lambda, as we can see here, is 2 pi over k. So if we replace lambda in here, we get that that's h over lambda, which is 2 pi over k. H over 2 pi is often written as h bar. It is the reduced version of Planck's constant. H bar is simply Planck's constant divided by 2 pi. times k. And so we've now shown that the momentum of the wave is Planck's constant, h bar, times k, the wave number, and k is 2 pi over lambda. Now I said earlier that the wave appears to move to the right, but in practice the medium in which it's travelling does not move. Think, for example, of ripples of water on a pond. You might, for example, throw a stone into a pond and you watch the ripples moving out in concentric circles. But if you were to put a piece of cork floating on the pond, what you would find is that that cork does not move in this direction, even though the waves appear to be doing so. All the cork will do is bob up and down in the water. Similarly, if you take a piece of rope and you fix it at this end, we shall do this again in a minute, and then you wiggle it at that end, you will create pulses that will go along the rope. You will actually see pulses moving along the rope. But of course the rope itself, that piece of rope there, that doesn't move. All that does is to move up and down. If you take electromagnetic radiation, something like light, it appears to be moving in, say, this direction. With the velocity, it will have the velocity c if it's light. But all this really is a variation in the electric and the magnetic fields. And all that is happening is that the electric field is oscillating up and down, and the magnetic field is oscillating backwards and forwards. The fields themselves do not move to the right. But by going up and down at varying stages, it creates the impression of a wave that is travelling, in this case, to the right. And the implication of this, which is not true, as we shall see for standing waves, is that all the way along the x-axis, if this is the x-axis, every point on this wave is oscillating up and down to give the illusion of the sine wave which is moving to the right. So now let's go back to our idea of the rope, which we're going to fix at one end and essentially fix at the other end by holding it. But the only concession I'm going to make is that I'm going to move the rope in a very small amount. I'm going to give it a bit of a wiggle. And when I give it a wiggle, I will create a wave in the rope which will move in this direction. And so that wave will move along the rope. Of course, as we've said, the rope itself, or the elements of the rope, don't move. They just go up and down. But that gives the impression of a wave travelling all the way to this fixed point. When it gets to the fixed point, it can't go any further, and it is reflected, and it's reflected upside down. And so there will also be a travelling wave coming back in the other direction. So you've got two travelling waves, one coming in this direction, one coming in that direction. And when they coincide, the waves superimpose. And that's basically just added together. So let's look at the formula for this travelling wave. We'll call it y1 is equal to the A, which is the amplitude, times the sine of kx minus omega t. That was the travelling wave we had previously. This wave we'll call y2, and that equals A times the sine of kx plus omega t, because the plus indicates that it's now moving to the left. And when we want to know what the total effect is of a superimposed wave, we get that y is equal to the sum of y1 plus y2, that should be y1 there, plus y2, which is going to be this term plus this term. Now this is where you need geometry. I was going to do this, but I decided not to do so. This is just mathematics. There's no physics in this at all. If I'm asked to do so, I'll do a separate video on how you can derive this. But from sheer geometry, you can show that a sine of kx minus omega t plus a sine kx plus omega t is, it comes out to be 2 times a times the sine of kx times the cosine of omega t. And that is the formula for a standing wave. It's when two waves are coinciding. So in the case of the rope, you've effectively got two fixed points. This point is absolutely fixed. This point I'm holding in my hand, and the only concession is a wiggle. And I can get to a situation where the rope is oscillating up and down like this. But that's not the only position that I could get that rope to oscillate in. I could, for example, have a situation where it oscillated like that. And then what would be happening is the rope would be going in alternate directions. And there are others. I'll just draw one more because otherwise it gets rather untidy and we can't actually see what's really happening. And in this situation, these two outer levels are going up and down, and the other is going down and up, down and up. So let's draw that again because it looks a bit of a mess. There we are, the wave with fixed at these two ends. These 2 points go down and up, this point goes up and down. So that goes down and up, that goes down and up, that goes up and down. So these are always out of phase. But you'll notice something about this wave, which is a standing wave, which was not true of the travelling wave. This point here and this point here never moves. The rope never moves up and down. It's constantly zero. These points here are moving up and down, but there are 2 points which are called nodes where the rope does not move. We don't call these fixed points nodes because we know they can't move. We have restricted them. We have clamped them so that they cannot move. But in theory, these points here could move, but in a stationary or standing wave, they actually don't. And we'll see why in a moment. If we look again at our formula for a standing wave, you'll see that you no longer have a kx minus omega t term. And it was the kx minus omega t that gave you the travelling wave. Well, there isn't a kx minus omega t anymore. This is just a sine kx times a cosine of omega t, and that's what makes it a standing wave. That's why it doesn't move, which is why it's called a stationary wave. But you will see that the amplitude of the wave at any position in x and any time t is going to be given by this combination of sine and cosine. Let's rewrite that down here. That it's going to be sine kx times the cosine of omega t. And we're going to look at each of those terms individually to see what happens to the wave as a consequence. First, we're going to look at the cosine omega t term. And we're going to consider that position when t is equal to 0. When t is equal to t, that's the period of the wave, divided by 4. When it's equal to the period of the wave divided by 2. When it's equal to 3.5 of the period of the wave. And when it's equal to, 3/4 of the period of the wave. And when it's equal to the period of the wave. So when t is 0, when it's period divided by 4, period divided by 2, 3/4 of t, capital T, and t itself. What happens to cosine omega t? Well, cosine omega t, remember I told you that omega is 2 pi f, so that is the cosine of 2 pi f times t, where t is the time in seconds. But f, I told you, was 1 over capital T, so that equals the cosine of 2 pi divided by capital T times the time in seconds. And now we can look to see what happens to this cosine term here, for these values of t. Well, when t is equal to 0, obviously you will have cosine of 0, and the cosine of 0 is 1. When t is equal to t over 4, then you're going to get cosine 2 pi over t times t, which is t over 4, and that will give you the cosine of pi over 2. And the cosine of pi over 2 is 0. Now we'll look and see what happens when t is equal to t over 2. You're going to get the cosine of 2 pi over t, that's this term here, times t, which is t over 2. The t's cancel, the 2's cancel, and that's going to be the cosine of pi, and the cosine of pi is -1. And then when t is equal to 3t over 4, the cosine term will become 2 pi over t times t, which is now 3t over 4, and that is going to give you 3 pi over 2, 1.5 pi. And the cosine, that's the cosine, of course. And the cosine of 3 pi over 2 is the same as the cosine of pi over 2, 0. And when t is equal to t, then you're going to get a cosine term of 2 pi over t times t. And that's equal to the cosine of 2 pi, and the cosine of 2 pi is the same as the cosine of 0, which is 1. So you can see what's happening as time progresses. This cosine term is oscillating from 1 through 0 to -1 through 0 to 1. And it will keep doing that. It keeps going from 1 to 0 to -1 to 0 to 1 to 0 to -1 to 0 to 1 to 0 to minus, and so on. That's the effect of the cosine term. Now, what about this sine term? Well, let's plot sine kx. Sine of kx will look like this. This is the y-axis, this is the x-axis. One complete wavelength is lambda. But what you'll notice here is that when x is equal to lambda over 2, that is a half wavelength, or when x equals lambda, that is a complete wavelength, the sine term of kx is 0. And the reason for that is that you'll remember that k was 2 pi over lambda. And so the sine of kx is going to be the sine of k, which is 2 pi over lambda, times x. And x is either lambda over 2 or lambda. Let's do it for lambda over 2 first. The lambdas obviously cancel, the 2's cancel, and you get the sine of pi, and the sine of pi is 0. If we do the same calculation for x equal to lambda instead of lambda over 2, then you're going to get that sine kx is equal to the sine of k, which is 2 pi over lambda, times x, which we're now going to take as lambda. Lambdas cancel and you get the sine of 2 pi, which is 0. In other words, at this point and this point, y is 0. And it will remain 0 at all points. This part of the wave may be going up and down, but these points here, which are the nodes, do not move. There is no oscillation up and down. They are 0 all the time. So now we can see what's going to happen to our wave. Here is our wave of sine kx. And remember, the nodes are fixed, they do not oscillate. But this will oscillate up and down. Why? Well, here's the reason. When this is sine kx, remember term? And we've got to multiply that by the cosine of omega t. That was the formula, or the essence of the formula for a standing wave. Now, when t is 0, we said that cosine omega t is 1. And so consequently this term, which is the sine kx term, times 1 just gives you this term. But when we move on to t is equal to the period over 4, we said that the cosine omega t term is 0. And that means you have to multiply all these points on the sine wave by 0. And if you multiply all points by 0, what you're going to get is a flat line. Now let's consider what happens when t is t over 2, half the period. We calculated that the cosine omega t term is -1. So now you have to take this sine kx term and multiply it by -1, which means that you'll get essentially the inverse because you're multiplying by -1. This was what you got when you multiplied by +1. This is what you get when you multiply by -1. And then finally, when t is equal to 3t over 4, we said that the cosine omega t term was 0 again. And that means that you're going to get every part of the wave will have an amplitude of 0 because the cosine omega t term will ensure, since that's 0, that the whole multiple is 0. And so you can now see why a standing wave oscillates in the way it does, because it's going from this position, all the points here are going down, all the points here are going up, until they all arrive at a value of 0. They continue in that direction, downwards and upwards, until they get to this position, and then they start to go the other way, until they get back to a flat line again, and then they continue in that direction until they get back to the starting position. And then they just continue doing that. So the cosine term is going from +1 to 0 to -1 to 0 to +1 to 0 to -1 to 0. It's the cosine term that is making this fluctuate and making each point on the sine wave oscillate. Apart from the nodes, which are already 0 by virtue of the sine kx term, so they have no impact on the cosine term. They will remain fixed at all points. So if we go back to our rope, fixed at one end, held by me at the other end, essentially fixed, but with just the flexibility of a little wiggle, I can create a situation where the rope is oscillating like this, and that's what's called the fundamental or the first harmonic. You can try this with a skipping rope, or you can get to a situation where the rope will look like this. In this case, it's just going down and up, down and up, down and up. There are no nodes because both of these ends are fixed, and where you fix something, it's not strictly a node. Here, this wave will go alternately up and down like this, but this point is a node. It will not move at all. If you wiggle it a bit faster, you'll get a wave that looks something like this, where you now have two nodes. This is called the third harmonic. This is the fundamental or first harmonic. This is the second harmonic. This is the third harmonic. These nodes never move. They could, but they don't. These points are fixed, and the wave here, these two parts go down and up. This part goes up and down. So this is going like this is going like this, and these two are going in sync. And of course you can have as many resonances as you like. There might be a fourth harmonic that looks like this. This goes down and up, this goes up and down, this goes down and up, this goes up and down. So alternate ones are going in sync, adjacent ones are going in opposite directions on the rope. Those are all standing waves, and they all have, of course, different frequencies. If the total length of the rope is L, then you can see that this is essentially just half a wavelength, and therefore in this case the wavelength is 2L. In this case, you've got one complete wave, and so the wavelength is L. In this case, you've got 1.5 wavelengths, and therefore the wavelength in this case is 2/3 of the length of rope. So this is 2L/3. And in this case, you can see that you've got two wavelengths here. One wavelength, which is this, is just half of the length of the rope. So the wavelength here is L/2. Now, the reason that standing waves are interesting is that they are essentially the reason that we have quantum mechanics. We always knew, or rather, as soon as we got into an awareness of these things, we knew that an atom could be described as a nucleus, which is positively charged, with orbiting electrons, which are negatively charged. The problem with this description is this, that if you have an orbiting charged electron, what we know about electrons that are in orbit is that they are accelerating because they're changing direction. They may not change speed, but they're changing direction all the time. And an orbiting or an accelerating charged particle emits radiation. That's, in essence, how television waves are transmitted from a transmitter. Electrons are accelerated up and down the transmitter, and the consequence is that broadcast waves are sent out for your television aerial to receive. So when an electron is accelerating around the atom, it should be radiating out energy. And if it's radiating out energy, it has to spiral in. And if it spirals in, it will eventually collide with the nucleus, and the whole thing will be obliterated. And it's calculated that that would happen in 10 to the minus 14 seconds, which is 100 million millionth of a second. So on this analysis, no atom can survive for more than a very small fraction of a second, which means you and I couldn't survive. So this isn't obviously the way it works. And it was the quantum mechanics people, in particular Broglie, who suggested that instead of thinking of the electron orbiting the nucleus as a particle, maybe we should consider it orbiting as a wave. And more than that, a standing wave. Which means that there is an integer number of wavelengths in the journey around the orbit. And if the orbit length is L, which of course is the circumference, if you like, of this orbit, which is the same as 2 pi r, where r is the radius of the orbit, then there are an integral number of wavelengths in that orbit. And any point on the standing wave remains the same. So let's assume a wave function for this wave. A simple wave function is equal to a times sine of kx. That's very simple. And what we're saying is, let's take a node on our travelling wave, and we say that that is represented by this formula here. Once the electron has gone all the way round, it has now gone x plus L, because at this point it was at x. Now it goes right the way round and comes back to where it started. It's now x plus L. So the wave function is now a times the sine of k into x plus L. But the rule is that that must be the same. Therefore, the wave function when it started and the wave function when it comes back to where it started must be equal. So a sine kx must equal a sine k into x plus L. And the only way that can happen is if KL is equal to an integral number of values of 2 pi. The reason for that is that, of course, if you've got the sine of any angle, sine phi, that is going to be equal to sine phi plus 2 pi, because you've just gone round the circle. Let's just illustrate that. here is an angle, that angle is phi. Do it like that, that's the angle phi. So you're here. If you go round a distance 2 pi, you essentially just go right the way around the circle and end up where you started. So the sine of phi, that angle, is equal to the sine of phi plus 2 pi. It's the same angle. So any multiple of 2 pi will have the same effect. So where we've got psi is a sine kx plus L, that's sine kx plus KL, KL has to have the value of an integral number. M is an integer, an integral value of 2 pi. So KL must equal integral value of 2 pi. But you'll remember that earlier we showed that the momentum of a wave is equal to h bar, that's reduced Planck's constant, times k, which means that k is equal to p over h bar. And if we substitute k into this equation here, we get that k, which is now p over h bar, times L is equal to m times 2 pi. And then if we put everything on the other side apart from p, we get that p is equal to m times 2 pi h bar over L. And I remind you that m is an integer. Now these are all constants, 2 pi, h bar, and L of course doesn't vary. So this is all a constant. And this is momentum. And what this shows you is, and this is where quantum mechanics is born, that the values of p have to be integral values of this amount. The momentum of the electron cannot just be any old amount, it has to be integral values of this term here. And similarly, angular momentum is momentum times r, it's a cross term, but we don't need to worry about that at the moment, is going to be the same because the p term is an integer value. It is quantized, and that is essentially the birth of quantum mechanics, that momentum of the electron cannot have just any old value, it has to have integral values of this term here. And that's what keeps the electron in orbit and not spiralling into the nucleus, because if it was spiralling it would have a constantly varying momentum, and this does not allow that. So it's using the electron as a wave rather than a particle, which gives rise to its momentum being quantized, and that's the birth of quantum mechanics. Hello, today in response to a request from a YouTube viewer, I'm going to give a little more information on standing or stationary waves. I have already covered the issue of waves, travelling waves and standing waves in my video Waves A-Level Physics, and the link to that, and in particular the standing wave section, is on the screen now. Before we look at standing or stationary waves, we first need to consider travelling waves. The formula for a travelling wave is that y is equal to the a, which is the amplitude, times the sine of kx minus omega t. I'll explain what all that means in a moment, but if we plot that graph, we will find that we get a sine wave, and the sine wave itself will travel. That's why it's called a travelling wave. It will move in this direction. Will divided by the wavelength of the wave. And that came from our quantum mechanics videos. Well, lambda, as we can see here, is 2 pi over k. So if we replace lambda in here, we get that that's h over lambda, which is 2 pi over k. H over 2 pi is often written as h bar. It is the reduced version of Planck's constant. H bar is simply Planck's constant divided by 2 pi times k. And so we've now shown that the momentum of the wave is Planck's constant, h bar, times k, the wave number, and k is 2 pi over lambda. Now I said earlier that the wave appears to move to the right, but in practice the medium in which it's travelling does not move. Think, for example, of ripples of water on a pond. You might, for example, throw a stone into a pond and you watch the ripples move past the fixed point. In other words, starting here, when this crest reaches this point, the time taken is the period. And finally, as I said, this entire wave is moving to the right in this way, and it is travelling at a velocity v. And we will be able to calculate the velocity in just a moment. Now this formula, we shall see, tells you everything you need to know about this wave. K in the formula is equal to 2 pi over lambda, where lambda is the wavelength. And omega in the formula is equal to 2 pi times the frequency, where frequency is the number of waves passing a fixed point every second. Now the velocity of a wave, that's v here, is given by the wavelength multiplied by the frequency. And the wavelength, you can see from this formula here, the wavelength, we'll see in a moment that it doesn't really move, it just gives the illusion of moving, but we call it a travelling wave. We've already said in previous videos that the distance between two peaks is the wavelength, lambda, of the wave, and that if you take a fixed position and you watch to see how many peaks go past in 1 second, that is the frequency, the number of peaks passing a fixed point every second. I should perhaps have explained that in this graph, this is the y-axis and this is the x-axis. The period of the wave, which is sometimes written as t, is equal to 1 over the frequency. The period is the time taken for one wavelength to pass the fixed point. So the frequency is the number of waves which pass in 1 second. The period, t, is the time taken for one wave to is 2 pi over k. So the velocity is the wavelength, 2 pi over k, times the frequency, which we get from this formula. Here the frequency is obviously omega over 2 pi. So omega over 2 pi. The 2 pi is obviously going to cancel, and that simply gives you omega over k. So when you have this formula, that y equals a sine kx minus omega t, then the omega and the k give you, omega divided by k, gives you the velocity, the speed at which this wave is moving to the right. I should just explain that the minus sign in this formula indicates that the wave is indeed moving to the right. If that were a plus sign, it would mean that the wave was moving to the left. We can even measure or discover the momentum of the wave. In our quantum mechanics videos, we have established that the momentum is Planck's constant